I'm going to start talking about the SPI because we need to understand that before we get to utilize the DAC. So we've done a lot. We've worked a lot with the asynchronous serial communication. SPI is synchronous communication. So on the asynchronous, we had two lines. We have the TX and RX. And so if this is your microcontroller, you have data that comes out on the TX line and it's received on the RX line. And when we looked at that data, we had we would have an idle line, and then we would have a start bit that was always low, and then we have 8 data bits. And a stop bit. And with the asynchronous communication, you had to pre-agree upon ahead of time with whoever you're talking to what the speed of these bits are going to be, what the width of the bit was going to be, and this was the bit rate. So SPI is very similar to this, except for it's synchronous. And because it's synchronous, that means we need more wires. Maybe we don't always need more wires, but with SPI we need more wires. So with the SPI, we're going to have similar ideas of RX and TX, but they call it SDO for serial data out, and SDI for serial data in. So this is similar to TX, and this is similar to the RX. But then we also have an SCK, which is the serial clock. And there's one other signal that's going to be a chip select. And so with the asynchronous, what you would have is you'd have one microcontroller talking to another microcontroller. This is what we're doing in the lab. There's other topologies that can be set up that are a little different, where you could have multiple devices. But we just, for the lab that we did, we just had 2 devices talking to each other. With SPI, though, you could have multiple devices. So here's your microcontroller, and you could have multiple chips out here. So in this particular lab, we're going to have a DAC. And the next lab, we are going to have an LCD display that is that we talk to using chip registers. So you have these 4 lines coming out of the microcontroller. And then the chip select line, it's a little special in that we need one for each chip. So for the SDO, we're going to be able to tap off and just hook all these lines in parallel. The SDI, same thing, and the SCK. And so this is some other device. It doesn't matter what it is. And then in order to select which device we want to talk to, there's going to be one line dedicated for each device that will be our chip select. the chip select for the DAC. This is the chip select for the LCD, and chip select for the whatever device. So when we talk to the DAC or the LCD, information only is going out of the processor. So the SDI line never even gets used. So the SDO is it's out of the microprocessor, SDI is into the microprocessor. And when the data is transmitted, you don't have the start and stop bits. It's just pure data. And so we would have they usually draw the idle line when they're in the data sheets for these type of parts. They'll draw the idle line showing both a low and a high condition. And the reason they do that is because it could be either high or low. On the asynchronous serial, when the line is idle, it's always high. But on these guys, the idle line can be high or low. And then we're not going to worry about the SDI right now. So this is just the SDO. And then when we're ready to start transmitting, we're going to have a clock that is going to possibly come high and then come low. And so when it transitions from high to low, or from low to high, our conditional will come from this unknown state of either high or low to some known state, which may be, we'll say we're going high. And then, so the setup happens on the rising edge, and the data is read by the receiving chip, the DAC, on the falling edge. So the data has to be valid on the falling edge. And then when the next rising edge comes in, the data will transition again. And on the next falling edge, it's read again. And so on through 8 bits. So we got 1, 2, 3, 4, 5, 6, 7, 8. And then so we have some data. Often they'll show this too in data sheets. They'll do kind of, we don't know what state you're at, or we don't know what the data is going to be, but we transition, and we can end up either high or low here, and again, we're going to transition again. We could end up either high or low. So we transitioned on this edge, and we read on this edge. We transitioned on this edge, and we read on this edge, and so on. This would be bit 7, 6, 5, 4, 3, and so on. So, in order for the receiving chip to acknowledge this data, though, there's a chip select line which is usually active low. It's not always active low, but I would say 95% of the chips you're going to deal with, this line will be low. So the chip select, sometime before we start doing any data transmission, is going to go low. And then after our 8 bits have been transmitted, it'll come high again. It's not always the case, but more often than not, we mentioned before when we're doing the asynchronous, the least significant bit is transmitted first, and then the most significant bit is transmitted last. For SPI devices, it's usually the most significant bit is usually transmitted first, and the least significant is transmitted last.